Greetings and welcome to a new video about MOSFET amplifiers. This is our example number 4. In this example we will look at the two-stage circuit, two-stage amplifier using the N-channel Enhancement MOSFET circuits. So we have two MOSFETs and we will discuss the amplification for this specific two-stage amplifier. Of course, we will work out in the calculations everything step by step and also verify these in the SPICE simulations. So let's look at our circuit. As said, we have now two transistors in our circuit, so it will be a two-stage amplifier. In the previous example, we have seen that we had only one transistor, for example, one MOSFET or one BJT. And this is a specific condition where we have two MOSFETs. It will be a two-stage amplifier. The MOSFET specifications for the M1 and M2 and also given in the circuit are shown here. So we have the parameter of the threshold voltage and the conduction parameter given here. We also have a couple of resistors. These are the resistors. We also see that the input Vin and with its own output resistance Ri is coupled through this complete circuit via the C1, which is the coupling capacitor. And the load RL is also coupled to the complete circuit using the coupling capacitor C2. Another capacitor CS is here required to couple or to bypass the resistor RS1 in order to increase the voltage gain. We have the values here, so it will be a VDD and VSS supplied circuit, so it will be a symmetric circuit, the 15 and the minus 15 volts. We also see the values of the resistor here. So what we want is the calculation of the voltage gain, which is from the input all the way to the output. So VO over VI. Okay, so how do we work this out? Let's look at the solutions. As said in the previous examples also, we have two analyses. One of them is a DC analysis, and the other one is the AC analysis. So we start with DC analysis for this circuit. In the DC analysis, we know that the capacitors will be an open circuit, so it will be only left with this part of the circuit. So you actually also assume for the operation of the MOSFETs that they are operating in the saturation region. So we have then a quadratic relationship for our drain current. But for that, in order to fulfill or satisfy the region of saturation, we need to also satisfy these two conditions. But we will check it afterwards. So we just assume it and we will check after this analysis that this is correct or not. This circuit here given here is the DC analysis circuit. What you see is, as said, the capacitor is open, so we will disconnect the source and disconnect the load. So we all see this. We also see the capital letters for the current. So the IG1, ID1, IS1. So this is a drain current and a source current for this part of the circuit. And also a similar case for the second part. The first stage is, by the way, a Common-Source Amplifier, and the second stage is called the source follower. We have discussed this in the previous videos in the separate circuits. Now, we know from the MOSFET that the gate current is always 0, so we have here IG1 and also the IG2, both of them are 0 amps. We see here the ID1 and also the ID2, but they are of course also equal to IS1 and also IS2. So ID1 is equal to IS1, ID2 is equal to IS2. So we would like to check that our assumption of the saturation region is correct and also require parameters to calculate the parameters we need in the AC analysis, which is our second step. So we start first with this first stage, which is this part. And we know from here that the VG1 with this node can be used or calculated using the voltage divider rule, because this node here, or the branch, has 0 volts, 0 amps here in the branch. It means it is an open circuit. So we can apply the voltage division formula, because it is this voltage node. We know that is then the R2 over R1 plus R2 times the voltage difference plus the VSS, because it's also level shifted by the VSS. Now if I now substitute the values given here, we have then exactly 0 volts. Why? Because this is half. It's 30, so you get the 0.5 times 30 will be 15. Minus 15 is exactly 0, so the gate 1, so at this node will be 0 volts. So it is effectively grounded at DC. Now we have also the Kirchhoff voltage law at the input, so we can apply here at this input, looking of course at the stage 1. we can say the following: VG1 is equal to VGS1 plus the voltage across the RS1, which is shown here in Ohm's law, and plus VSS. Now that's the complete loop. Now we can also say, since we assume saturation region of operation, the ID1, this drain current, is equal to Kn1 times the VGS1 minus the threshold voltage quantity squared. This is all for the stage 1, for M1 MOSFET. When we say that the IS1 is only equal to ID1, which is true because the gate current is 0, we can substitute this in here for the IS1 because they are equal to each other. Then we get the following expression. So VG1 is equal to this. Now you see the following expression is actually appearing because this is 0 and VGS1 is unknown. The resistor and the Kn and also the threshold voltage is also unknown, and also the VSS. And this equation now has only one unknown, which is the VGS1. If I replace this minus 15 to the left side and also make this 6, I get this equation. And we can now solve this by hand or using the solver in our calculator. We have then the following results. One of them is the minus 0.613 and the other one is the 2.4465 volts. But this is less than threshold voltage of 1 volt, so this is not valid. So mathematically correct, but it is not possible in this circuit. And this is larger than the threshold voltage, and this is definitely what is valid. That's also one of the conditions to satisfy the saturation region. So we have it for the first condition. Now, so we take the VGS1 as 2.4465 volts in our future calculation. That means now we can calculate the drain current, because drain current has now 0.003 for the Kn1 times the threshold, the VGS1 minus 1 for the threshold, it's quantity squared, and you will get 6.277 milliamps. Now we now apply the Kirchhoff's voltage law at the output loop, so that's actually from here all the way down, in order to check the VDS1. That's actually the check for this second condition. So we can say VDD is equal to this voltage using Ohm's law, RD1 across RD1, plus the voltage VDS1, plus the voltage across RS1, plus the voltage at this node, which is VSS. Now we can now express the VDS1 as shown. And since the RD1 and also the RS1 has the same current, so we can group them together, that's shown here. Now when you substitute the values in here, you will get 4.892 volts. So just use the values we have determined for the current and also the given values here in the example. But this must be larger than VGS minus V threshold for the stage 1. And is that true? Yes, because 2.4461 minus 165, minus 1 will be down 1.4465. So definitely this 4.892 is definitely larger than this value. So again, a valid, so our assumption was indeed correct for stage 1. Okay, now we have the required values for stage 1. Let's summarize them here. Then let's now move to stage 2, which is then this stage. Still, we use the DC analysis. Now we can say this node VG2, which is at G2, can be calculated again, making the loop using Kirchhoff at this node is equal to the voltage across RD plus the voltage at node G2. That's actually shown here. And rewritten, it means VDD minus the current through the RD1 times the current ID1. That's shown here. When you substitute values, we of course have calculated already the ID1 from the first stage. And you get RD1 as 2000, which is shown here. And you do math here, you get 2.446 volts. Okay, now we apply the Kirchhoff voltage law at the input loop, which is this part. Now with this node, VG2, we have then VGS2 plus this voltage across RS2 plus the voltage VSS. That's shown here. Again, you make a loop. Now the drain current now for the second stage is again the same thing actually as for the first stage, but we use now the subscript 2 for the second stage. When you combine this, substitute this ID2 in here for IS1 because they are equal, because it's a symmetric device, we get the following expression. Now we can now substitute the value for VG2 and also VSS and also the resistors and also the parameter for the process, conduction parameter, and also the threshold voltage. So we get the following. Which you again see that the only unknown here is the VGS, so specifically VGS2 for the second stage. When you bring this minus 15 to the left side, you get 17.446, and also 4000 times 0.002 will be 8. Now you will have this expression, and again you can solve this by hand or using the solver in your calculator or any other solver. Now, when we do that, VGS2 will be one of the solutions is minus 0.498 volt, and the other one will be 2.3727. But this is less than a threshold voltage of 1 volt, so this is invalid. And the other one is larger than 1 volt, so this is valid. So that means our solution for this part of the stage 2 is then the VGS2 is equal to 2.3727. Now, since we have now our VGS, we can again use a drain current formula to calculate the drain current using the specific Kn2, and we get the value of 3.768 milliamps. Now we can apply now the Kirchhoff voltage law at the output to check the second condition, because the first condition is now met. Now we can set up the equation. We can say VDS2 and VDD, and also the voltage across the RS2 and also the voltage across VSS. So we can see that here, because the total voltage at this node is voltage this one plus the voltage across RS plus VSS. In order to get the VDS2, we can rewrite this equation again like this and substitute the values. You get 14.93 volts. That is definitely larger than the VGS2 minus V threshold 2, because that is only 1.3727. So again, we have a valid condition here. It means we again fulfill the condition of saturation region. So our assumptions for both stages are correct. Okay, let's now summarize the result for the DC analysis. We get the stage 1 and stage 2 results here, and this is the circuit we have used. And again, we assume our assumed saturation region is correct. Let's bring it here and now look at the DC analysis in the simulation results. So we will check that this is the complete circuit, including the capacitor, but we only look at the DC analysis. You see in blue the values for the measured gate to source here, drain to source, the drain current, and also similar for the second stage, etc. Now what you see is the ID1 here is exactly as we have calculated. VDS1 is very close to what we have calculated, so there's a small error. I think that's just due to the rounding off error. We have this 2.446 VGS1, so also very close to what we have calculated. This is the VDS2, 14.93 we had, so it is also very close to what we have calculated. This is also this VGS2, also what we have approximately, and also the ID2, which is also very close to what we have calculated. Actually, in this case, exactly what we have calculated. So it is a nice verification, confirmation that our DC values results are correct according to simulation. So that's all perfect. So let's move on now with the second step, which is the AC analysis. And we first set up the AC model or the small signal model. Now for the first part, for the M1, we have this VGS1 and also the dependent current source here, which is dependent on this VGS1. You see the source of the M1 is shorted because the capacitors CS is shorted. So all capacitors are shorted in the AC analysis. So this will be shorted. And also the DC current, DC values, DC voltage sources for powering up the circuit will be also shorted. So this is ground, AC ground, AC ground. That's why you have this shorted here to ground. That means the RS1 is actually out of the picture. That's why we have the source one is directly connected to the ground. This is all AC ground. You see also this R2 is going to ground because the VSS is AC ground. But it's also the same for R1 going up to ground. So they are effectively in parallel. That's why we have here this parallel combination of R1 and R2 at this node G1. You also see the RI and going to the VI, which is our input voltage source. Now we have now the drain 1, this is this node, but that is what we have here, which is then RD1, which is also going to ground because that is also AC ground. So that's why we have it there. Now D1 is directly connected to the G2, which is then the gate 2 of the second stage, so the M2. And at this node, we know that the source, the drain D2 is connected to ground directly. That's why you see it here. This is the dependent current source again of the MOSFET, but now for the GM2 and the VGS2. So the GM2 and also the GM1 needs to be calculated. We will do that shortly. We also see the RS2 here, which is going from source to AC ground, and also shorted C2 because of the AC analysis, and also RL because they are now effectively in parallel. That's what you see here. And we measure the voltage at the source of M2. Okay, and there's the current here, IS2, which is exactly the same as the ID2 because this is an open circuit. Now we need to develop now the equations to get the total voltage gain. But the total voltage gain is actually a product of three terms. Now, one of them is, let me go back, is the gain from the input, Vi, to the node voltage at G1. That's just actually voltage division, so look at this input part. Now, there's also a gain going from the node voltage G1 all the way to the D1, which is the common-source amplification circuit. There's also another one because that's going from the D1 or the G2 all the way to the S2. That is actually source degenerated gain or the source follower gain. So we can split the problem actually, which is a large problem, which is the total voltage gain, in three small problems. One of them is then the first, which is then let's say the A0, which is just an attenuation because it's going from the Vi to VG1. That's shown here. That's the voltage divider, so it is actually attenuating. Then the A1 is from here to there, so from G1 to D1, but that's just a common source amplification, so there will be some amplification there. That will be also inverted. We have seen it also in the previous videos. And we have here the A2, which is then for VS2 over the D1. So that's actually here, and that's the source follower. So we have seen these circuits also in the previous videos. So we can say now the total voltage gain is this expressed, but it can be multiplied by three terms. So A0, A1, and A2. So let's do that. Let's do that as we have it here, and then determine the specific parts here. And we know that the VO is also equal to VS2, so we can just simplify this or rewrite it in this form. What you recognize here is that this expression is exactly the same as this expression. Why? Because you can divide either VDE1 here, VD1 from the numerator and denominator, and also VG1 and VG1 here. So we only have again VO over VI, the same expression where we started. Okay, let's bring this again together. Now we look at the voltage divider expression. This is this gain, but it's just this parallel combination over the Ri plus the parallel combination. That's just a voltage division, so we have some factor here, which is less than 1. So between 0 and 1. The other one is the common source amplifier, and for that we have a standard formula which says VD1 over VG1. So this node voltage divided by this node voltage is equal to the minus the GM of this transistor times the resistor which you see here, but it's only now RD1. That's this. Now for the source follower we have also a similar formula, which is then given by this, which is V over VD1 or G2. That's GM2 for the second stage, so the MOSFET GM2, times the parallel combination here, and divided by 1 plus this same term, so that is the source degeneration for the source follower. Now we have now three equations for this total gain AV. Now we can now substitute that in here. So the blue is for the attenuation, red is for the common source, and the green is for the source follower. Now we can bring them together in some nice review. You also see that minus sign because of this common source amplification, so we still have an inverting action or inverting amplifier. And this is the complete expression for our amplification factor, so we need to first determine the GM1 and the GM2 in order to calculate the numerical value of this AV, the voltage gain. So let's do that, but for the GM1 and GM2 we require the DC values, the DC current, and also the process parameter, the conduction parameter Kn. This is the formula for the GM, and now for the first stage specifically we have GM1. We substitute the values for the drain current and also the Kn1 given. Now we have this 8.679 millisiemens. In a similar form for the ID2 using and then GM2, you get now this. So how much is that? For 5.490 millisiemens. Now we also need the parallel combination of R1 and R2. That's just these two resistors, 1 mega ohm and 1 mega ohm. That is, of course, parallel combination will be just the half, because they are equal to each other. It will be 500 kilo ohms. The parallel combination of RS2 and RL is just looking at 4000 and 6000, will be just 2.4 kilo ohms or for 2400 ohms. Now we have everything in order to substitute in here. If you do that, then we get the following result, which is then minus 16.1 as the gain. Okay, this is the voltage gain we have for this two-stage amplifier. Okay, let's bring it here and look at the transfer response. So we apply some input, which has some specific input voltage shape, pure sine wave. It has this 10 millivolts peak and also 10 kilohertz frequency, this blue line, and it has peak then 20 millivolts. But looking at the output, which is red, which is inverted, so you can already see this a minus sign here, it's inverted. It has a maximum and a minimum value we have determined here after a couple of periods. The peak value will be then 322.32 millivolts. That's the peak output voltage. Now when we do the voltage gain, we place a minus sign because of its inversion. We then do peak output voltage divided by the peak input voltage. Looking at the two values here and also the input peak voltage, you get minus 16.1 exactly, or a little bit larger actually, but that is very close to that one. And you see that this is really confirming with our calculation. So this is a very nice result. So from the transient response, we have verified that indeed the gain value is correct. Now let's also look at the frequency response, because there's a very interesting thing about that. This is the Bode plot, and we see the mid-band gain here, which is this value. But why is this 24.145 dB? Now you use this formula and you take the absolute value of your voltage gain to calculate your gain. And if you do that, you will get 24.14 dB, very close to what we have here. So again, the confirmation that the gain is correct. There's also another parameter, which is the lower cutoff frequency. So this is correct, but there is also a lower cutoff frequency. And lower cutoff frequency, FCL, denoted by FCL, will be dominated by the impedance looking into the source of M1, there's one. Because it's for the first stage, and the source, the impedance looking in here is the RS1 in parallel with the 1 over GM1. So for this, we need to calculate that using this formula, which is 1 over the 2 pi and the time constant. The time constant is the product of the CS times the impedance seen by the CS, which is the parallel combination of the transconductance here, 1 over GM1 in parallel with RS1. Now, what is GM1? We already calculated that, so we can also rewrite this here. So we can also rewrite this cutoff frequency like this. So we can see that this is the expression. And now we can determine the or we can find the GM1. What is GM1? GM1 was this value. We have determined that in our AC analysis from DC current ID1. When you substitute this value here, in here, and also the RS1, and also the others for the capacitor, because it was 10 microfarads. Let's do that. First the time constant, and then the cutoff frequency for the lower part. You will have 146 hertz, and we have here 145.7 hertz. So really close to what we have calculated here. That's also again a confirmation that this is indeed correct result. Alright guys, we have now verified our calculations for this two-stage amplifier using the two MOSFET N-channel enhancement MOSFET types. We have discussed the DC analysis, and from there we use the AC analysis circuit to get the required voltage gain. And from there we have also looked at the transient response in the simulations, also the frequency response to determine the gain and also the cutoff frequency. And this is the complete analysis, also similar to other amplifier circuits we have discussed in the previous videos. If you have any questions, comments about this example, please let me know and I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.